All right, for our next question, number 2 here, we're asked to calculate the energy of one photon of this taupe light. And we can use E equals hc over lambda is a good equation to use here because we've been given wavelength instead of frequency. So h is given here at the top, 6.626 times 10 to the minus 34 joules seconds. 3.00 times 10 to the 8th meters per second. And then finally, again, we'll need this wavelength to be in meters instead of nanometers, and that works out to be 5.8442 times 10 to the minus 7 meters. Transform it from nanometers into meters. Okay, and I get an answer here of 3.40 times 10 to the minus 19th joules. But it's going to be useful for us later, so let's go ahead and add a description there. That's the joules per one photon. Be useful in one of the later parts here. Both the later parts. So 3.40 times 10 to the minus 19 joules per one photon. So what's the energy of 1 mole? What's the energy per mole? So 6.022 times 10 to the 23rd photons, that's Avogadro's number, is 1 mole of photons. So now I'm doing 3.40 times 10 to the minus 19 times 6.022 times 10 to the 23rd. Gives me 2.05 times 10 to the 5th joules per mole. So for every 1 mole, there's 2.05 times 10 to the 5th joules of energy. And then there's a couple ways we could do this one. So I can just go ahead and say 1 kilojoule is 1,000 joules. Save myself a step, so 1,000 joules. And then it asks how many photons would it take to equal that amount of energy. I'm going to use this and I'm going to flip it over. So 3.40 times 10 to the minus 19th joules for 1 photon. Joules cancel, and then this will tell me now how many photons I need. So 1,000 divided by 3.40 times 10 to the minus 19 equals 2.94 times 10 to the 21st power photons. So a lot of photons required to get 1 kilojoule of energy.